we're going to start with some transportation problems. So just to give you a general idea of what a transportation problem in terms of linear programming is like, is the basically we have a set of factories or some set of suppliers, and we want to know basically how we want to distribute. These factories, these factories or suppliers are basically producing like, let's just say, a single product for now. And what we want to determine is that how do we want to optimize the transport, like from each factory to each of the stores out there, or to each of the customers, such that we have enough supply, and that we want to satisfy all the total demand. So effectively, you could also be kind of thinking, well, yeah, it could probably decide this easily for an example such as small as this one. But when it comes to, say, multiple factories, multiple warehouses, and multiple customers, multiple stores, we're gonna want to try and figure out, like, say, what we want to try and minimize a few different things, and this can come in different forms. So, for example, we want to minimize the cost of transport, which can sometimes also be measured in terms of minimizing the distance that the transport has like the distance that the trucks carrying the items needs to transport and things like that. So we'll look at a more specific example, but one of the other things I want to stress before we go on is that the transportation problems can also kind of just be modeled in different situations, and sometimes it's not really so much trucks carrying things from a factory to a store. It can be something quite different. And when we go to this next, when we go to this first example, you kind of see what's happening. So here in this example, we've got, okay, Adelaide has two water catchment storage facilities, or you can think of, and basically this is kind of more like a water supply thing. So you could probably think like, okay, well, we've got two places that catch the rain, and then it supplies the water through the pipes to three different dams. So a dam is kind of like another way. I don't even know how to describe a dam, but think of like, I guess, another kind of water catchment that helps distribute water throughout a given area. So here in Adelaide, down here in Australia, if you're watching this in a different country, so effectively what we have here is that we've got a transportation problem in terms of how do we distribute water to from our two storages to three different dams, such that we've got enough supply and we satisfy the demand. So now, what we've got up there is that we've got the distance between in the bottom table, we've got the distance between storage facilities and the secondary dams. So what's happening here is that, okay, we want to just try and minimize the total distance. Um, so effectively, transportation problems can be relatively simple in that respect. So usually one of the first things you want to do is kind of actually expand the table, or and some others might not be. Depending on how transportation problems are taught, the approach might be a bit different for some people. So I'm kind of just showing a few things. So the table here, the distance between storage facilities and secondary dams are in kilometers. So, and then on the left, I want to say supply, and then it says I also want the demand of the dams. So some tables will kind of give you that information already in the table, but for this one, not so much. So storage one could store up to 400. Storage one can store up to 500 megaliters. So we're just saying megaliters. Just making sure that's appearing on the recording. Okay, and the demand of the dam. Dam 1 needs 300 megaliters per day. Dam 2 needs 200. And Dam 3 needs 400. And then all the numbers in between is basically the distance. So I don't know if the distance are in kilometers. Okay, so that's in kilometers. Okay, so the first thing I want to check is that I want to make sure that the supply equals to the demand. And you probably think, well, why are we doing this? This is kind of an extra thing that is usually introducing transportation problems, in that, or in this case, a balanced transportation problem, in that the supply must equal to the demand, and that's one of the first things you want to have to check. So, in this case, just summing up the demand, summing up the supply, we can see that the supply plus demand is equal to 900. Therefore, it is a balanced transportation problem. So The main reason that we want to try and distinguish between balanced and unbalanced is that the unbalanced transportation problem usually might need a little different approach. But in this case, this is a balanced transportation problem, so it's going to be reasonably straightforward. So what we're going to do now is that we can model this as a linear programming model now using the information in the table that we've constructed. So now the way I want you to think about the I guess so one thing I'm going to think about first is the objective function. And since the objective function, what we want to do is that we want to minimize the total transport distance. So if we want to minimize each of these numbers, and then let's just say, even though it might not technically be a correct way of looking at the problem, let's just say that each megaliter of water going through will be like 1 unit, and then it's going to be 1 unit multiplied by that distance. So it's sort of like we want to minimize the overall traveling distance. So the way to look at it is that if we define the decision variable, and we only need one, so we only need like to actually define one thing, but it will actually cover all the different connections. So we'll start by defining a decision variable xij, which is defined as the number of megaliters of water transported from, in this case, storage excuse me, I can't spell facility in my head, my apologies. Facility I to dam J. So and then because we're kind of indicating I and J, so notice that we got Xij. It's got two sub letters, which refers to where I is referring to the storage facility and J is referring to the dam. So this adds a extra dimension to the variable, and then we'll eventually see where that comes in. So now when we define those decision variables, we definitely want to clarify that I is an element of, in this case, the storage facility. So this is just storage facility 1. So there's a few different ways you can name it. So we can say I is equal to 1 or 2, and in that case, that will basically be, sorry, let me use a different color. So basically, that will be storage facility 1, and then 2, and then we can also specify J is equal to, say, 1, 2, or 3, and that effectively is referring to dam 1, 2, or 3. So, and that's basically where we have the subset. So the idea here now is that when we write our objective function, we can have the storage facility of 75x11. That's basically the amount of megaliters transported from storage facility 1 to dam 1. We represent it x11. And then in a similar way, we got x12, x13, x21, x22, x23. And basically our objective function is that we can just add them all up. So in this case, the objective function as we said here, is that we want to minimize the total distance, which in this case is going to be equal to all these numbers added up. So, and we'll write those out explicitly. So it's gonna take me a while. 75 plus x11 plus 40 x12 plus 85 x13 plus 20 x21 plus 55 x22 plus 75 x23. Okay, so that's our objective function, and looks like we're gonna need another page, so I'll just quickly do that. And then now that we've done the decision variable, the objective function, we want the constraints. So in typical transportation problems, there's two different types of constraints. There are supply constraints and demand constraints. So in this case, the location I just want to double check something. Up to 400 megaliters per day. Okay. So and then we want to clarify the supply. Okay. So the way to think about the constraints is that when the amount of water coming out of storage facility 1 cannot be greater than 400. So let me write the supply constraints. So now if we look at storage facility 1, so I'm just gonna be a bit more facility 1. So in this case, storage facility 1, so all the water that's coming out of storage facility 1 is represented as x11 plus x12 plus x13. So, and then all that, the sum of all that is going to be less than or equal to 400. So for storage facility 1, the supply constraint will be x11, x1 plus x12 plus x13, and then it's going to be less than or equal to 400. And then similarly for storage facility 2, we have x21 plus x22 plus x23, which is less than or equal to, I think it was 500? Yes. Alright. So now we've got the demand constraints. So notice how with the supply constraints, what we've done effectively is that we've gone across each of the rows. So for the demand constraints, what we're going to be doing is that we're actually going to be going down the columns this time. And this is one of the research transportation problems. Seem relatively easy to model, but it's also more introducing you to problems that have a larger dimension. So in this case, so it's for the demand constraints. So we got dam 1, and then dam 2, and then dam 3. Okay. Looks like the recording's a bit slower than my voice, so I do apologize for the delay. So in this case, now we can think about the amount of water going into dam 1. So in this case, it would be x11 plus x21, and then we're gonna meet the demand, so it's gonna be greater than or equal to the demand amount. So in this case, for dam 1, that's gonna be x11 plus x21, which is greater than or equal to 300. And then similarly for dam 2, that's 12 plus x22, which is greater than or equal to 200. And then x13 plus x23, which is greater than or equal to 400. And then of course, don't forget our non-negativity constraints. And I'm just going to write this in a more condensed way, so that's going to be xij is greater than or equal to 0 for all I and j. Okay, and that's pretty much it for our basic balanced transportation problem. So the kind of the main points is basically for the constraints, that's the supply constraints and the demand constraints. Make sure you know which way to read across the table, and effectively all the decision variables basically cover all the different possibilities, but we can effectively use a single letter, but that has more than one dimension. So we'll look at a different transportation problem in the next video. So until then.